Hello and welcome to our training today presented by Deluval Software. Today we'll be working in our structural analysis and design software RFEM 6. So this will be a 2-day training, taking course for a couple hours today and a couple hours tomorrow, geared at universities, including students, professors, and instructors. My name is Amy Heilig. I'll be just giving a brief introduction today for this training. I'm the CEO of the U.S. office located in Philadelphia, Pennsylvania. I'll then turn it over to my colleague, Alex Bacon, who will be your trainer. He's a technical support engineer, also located in the Philadelphia office. And finally, we have Siska Choa, who will be helping out with all questions today. She's a technical support engineer, also located in Philadelphia. So if the control panel does seem to get in your way when you logged into this GoToWebinar, you can certainly hide it with the orange arrow up at the top. But we want everyone to ask questions throughout this training, so you can actually do so within this dialog box under the questions options. So Cisco will be helping out with those questions and Alex will be answering them at the designated breaks today, but as they come up, feel free to type them into this input box here. So I just want to briefly explain the program configuration option. So RFEM 6 is the base program. This allows us to fully integrate with BIM software such as AutoCAD, Revit, Tekla. You can fully model your structure, you can apply loads to the structure, and finally you can run a calculation to get the full analysis. So from the analysis, we would get information like deflections, internal forces, support reactions. But in addition to this, we have multiple add-ons. And the add-ons that we have, you can see a few of those listed here. This is not a full list, but just a select few, allow us to carry out the design. So for example, for steel, concrete, or timber, we have the US codes, the Canadian standards, and other international standards to take your structure and to actually carry out the design process. Now we have several other add-ons as well, for example, dynamic analysis, stability, and so on. It should be known that with the university or student licenses, you do get access to RFEM and all add-ons that we have to offer. So universities, including professors, students, instructors, all have access to a free full RFEM 6 license. And as mentioned, this is not only the base program, but all additional add-ons that we offer as well. Now, the licenses should be used for teaching or learning purposes. If you are wanting to use it for something like funded research, we certainly have options for that for different licensing. So feel free to contact us either through email or phone to discuss the options there. But alternatively, with teaching and learning purposes, free full licenses are provided. Now, this can be installed directly on your personal computer. So for example, if you're a student and you have your own personal laptop, we can provide access to that license directly on your laptop. But also, the license can be installed on a school computer. So for example, if you're a professor or in a lab type setting, if you need access to 20, 30, 40 different licenses in a lab setting, we can certainly accommodate this as well. The licenses will be valid for 1 year. After that year, there is an opportunity to renew as well for the upcoming academic year. We also will provide access to all program updates. So we currently come out with a release every week with RFEM 6. So as a professor or student, you'll have access to the latest program version throughout that year. We also provide free email technical support. So if you have questions while you're working through the program, any technical questions that you might have, you can email us at info-us@deluval.com and we'll be happy to help help you. So if you are wanting to request a license, you can do so directly through our website at deluval.com. Up at the top of the page, there is an education tab you can click on that allows you to request access to an RFEM 6 license, whether you're a professor, instructor, or a student. And with that said, I'll go ahead and hand it over to Alex now to continue on with the training.
Great, thanks Amy for the introduction and all of the info and details on that. So today, well, this is the content over for the 2 days, for today and tomorrow. We'll first start out with going over the basic principles of FEA, and then after that we'll go into our first model example, and I'll go over the basic UI and everything of RFM, and then we'll get into this continuous slab example where we'll go over FE mesh and plate theory and learn how to draw surfaces and create members. And then towards the end of today, we will probably start the design add-on example, which is the example you're looking at right now on this slide. And this is where we'll use this example to go over a couple other elements with regards to modeling. But the focus of this example is to learn how to use the design add-ons, and we'll just go over the basics, and we'll be designing timber, concrete, and steel. So there will be one break at the 1 hour mark for 5 minutes. And during that break, like Amy said, any questions that can't be answered in the chat, I'll ask Siska if there's any larger questions that I can go over during this break. So there, 5-minute break halfway through, and then we'll have another discussion period at the end of the 2 hours. I do have a question, and if you could just post it in the question section of the GoToWebinar panel. Do you plan on modeling along? And this will just help me know what the pacing should be for today. If you have another screen that you can work with, if you're planning on modeling along, that is an option. And I do want to also mention that if you're modeling along, I can't stop and help you with any of your modeling inquiries. So yeah, if you could, if you could post that or in the question section, then I can get an idea of how the pacing should go. I'll just give everyone a half a minute or so, maybe looking for the question section, but I see, thank you, Mary. No. Okay, all right, awesome. Well, I'll go at a normal pace. So thank you for participating in that. Thank you, all right. Next question. How much have you learned about FE yet? FEA yet in any of your classes? You can post yes or no. If you haven't learned anything about FEA yet, then no. If you have learned or you have a general knowledge of FEA, then if you could put yes or no in the questions again, that would be great. Okay, yes, okay. It's used to, yeah. All right, so half and half, it seems. Nice, okay, good. Thank you guys for participating in that. Great, so this is good to know. Either if you have learned or you haven't learned about FEA yet, I think everyone will find something in this presentation and training. So great, thank you guys for doing that. So yeah, let's just start. So we're going to start off with the basic principles of FEA. So First, computer software, that includes our software, is based on the displacement method. So if you haven't learned about FEA yet, or you have learned about it, there are two basic methods for FEA. The most common method and the method that RFEM uses is the displacement method. And this method is where the displacements or the deformations are the unknowns in the system of equations that we use. And therefore the displacements are calculated. So all other results, and then all other results like forces and stresses, are then calculated in the post-processing. So then there's the second method, which is the force method. And this is kind of the opposite of the displacement method. And this is where the forces are the unknown. And then afterwards, the displacements are determined in the post-processing. So most use the displacement method, just like RFEM does. So also, analytical solutions are difficult when it comes to large, complicated structures. So real structures require pages and pages of calculations compared to the simplified examples that are normally shown in structural analysis classes and static classes. And so this is why the FEA method was developed, and because so we can decompose those structures into a mesh of finite interconnected elements. And this is when a lot of smaller elements are used, and with standardized stiffness parameters. Structures are modeled and converted into finite interconnected element mesh. Material and cross-section properties are then given at each of these FE nodes. And these standardized stiffness relations can be described in a small equation at each of these nodes, which is then solved very quickly. Each of these smaller equations are solved very quickly with computers very easily. So that's how we get very quick solutions for these easy equations. Mechanical behavior at these nodes is then transferred between elements. So you can say this is how the properties are described as a continuum at each of the nodes. And then approximations are used to describe the mechanical behavior, which is basically what we learn in physics and our mechanics classes and things like that. So that's kind of the gist on how the FEA method was created and how it works. So this last word down here, discretization, I think is a very interesting vocabulary word. Discretization, the meaning of it, it's almost a verb, or it is a verb. Structures being submeshed into finite elements. So basically these large complicated structures, you would say, are being discretized or using discretization, which is structures being submeshed into finite elements, basically. So that's a word that's used in FEA terminology. So here is the FEA calculation workflow. You can see in the diagram on the right-hand side, this is kind of the cycle, basically. So first, we take the structure and we break it down into a mesh, or we mesh the structure, and we determine the local element stiffness properties. And then the next step, there we go. The next step, then the stiffness properties are transferred to a global coordinate system, and you get those stiffness relationships for each of the elements. And then these are assembled to get the global stiffness matrix of the whole structure. So this is our big system of equations that the computer then solves. Fourth step. So this is very important. This is where we add in, we implement our support conditions, or we add in our boundary conditions in the form of supports or external forces. And then the computer can then solve this system of equations and determine the displacement vectors. And last step, once the system of equations is solved, then the internal forces are calculated as part of the post-processing. So you get your internal forces, your deformations, and all of the static analysis results that you're looking for. And that's the end of it. So that is the FEA calculation workflow. And next, I have a question that, again, if you guys could answer in the chat, that would be great. So the question is, what is discretization? You got 3 choices there, and you can just type in A, B, or C, and I'll just kind of get a gist for if everyone's on the same page. Okay, so it looks like a lot of you guys are saying C. So the correct answer is actually A, a structure that is converted into finite elements. So C, submeshing finite elements into smaller elements. Yeah, I could see how that's, I could see that's a little like confusing at first when you read it, but yeah, the correct answer is A, a structure that is converted into finite elements, discretization. So good. All right. Now we can get into our first example and hop into the program. So this first example is going to be this model right here, very basic. Just for example purposes, we call it a continuous plate example. The topics that will be covered will be FE mesh design, convergence behavior. We'll be comparing the beam element to the surface elements and seeing how those two compare and how they differ. And then we'll go over FE mesh size and how and what the best FE mesh size is, or how to determine what your FE mesh size should be. And then we'll get into some results such as distribution of internal forces. We'll go over shear stiffness, which is going to be a big topic. And then we'll go over the result smoothing as well. So I'm going to switch into RFEM. And now, cool. Yeah, so this is RFEM. This is our FEA program that Amy just spoke about. And right now we're just in the base program. And I have that model, that example model open right now. This is what we're going to model in this first part of today. So right now I just want to go over the GUI or the user interface. So I think the 3 main important sections of our program is we'll start with our panels here. So I have the navigator panel here. Then this is the tables panel down here at the bottom. And then for results, this panel is our control panel on the right-hand side. And so these are the 3 main panels along with the toolbar at the top. And we'll start by going over this navigator panel left-hand side, which is probably the most important, useful panel here. This is where this is basically where the whole entire model is organized into these folders here. And each of these folders, if there is an arrow next to them and you can expand it, you can see we have our materials for this whole entire model, and we have our sections, thicknesses, and nodes, every single node. And when you click on one of these, you can, you can kind of see that it highlights that material. So all of these are highlighted. And yeah, so this is basically where everything's organized, and we'll obviously be getting into this in more detail as we start modeling. But mainly there are 4 tabs at the bottom of this panel. So right now, this is our data. This is all of our data. We're in our data tab here. All of the model data is organized here. But then we have our second tab, which is our display tab. And under the display tab, this is where, so if I right click, I can collapse all of these. And this is where you can turn on or off basically any graphics that are displayed in the work window here. So I could turn off, I can turn off the results. So if I uncheck model, then all of these graphical display objects here are turned off graphically. Our model is still technically there, but just graphically it's turned off. So if you want to turn off certain things like lines, nodes, members, you can turn those off here. So this is where anything you want to control graphically, you can turn on or off graphically in this tab. Third tab here is our views tab, and this is where you can control what you're viewing in the graphical area here. So down here, visibilities, you can turn this on, and now you can see the model is all gone. Let's say we only want to show members and we only want to show the members that are made of concrete. We can check that on. And so now you see this member made of concrete is now the only thing shown. So that's kind of how the visibilities works. If you have a very large model, you can use this to kind of just find what you're looking for or just display what you're looking for. So we'll just turn that off. And then up here, you can create your own custom user-defined views. So you can click this button and create a new user-defined view and have those created here. So pretty handy. And then if I turn our results back on, we have our fourth tab here, which is our results tab. And right now you can see we're looking at our static analysis, which is giving us our global deformations, and we can go through and turn on results for members and results for surfaces. So this results tab is basically where you'll be living if you're analyzing your model and you're checking on and off results that you would like to see. Next, we have at the top our toolbar, which is, you can see all of these buttons at the top. You can organize these buttons any way that you like. You can move them around. You take them out and put them in and put them wherever you want. I usually just, you can right click anywhere in this space up here, and you can hit restore default layout. And basically it'll put the buttons or the tools in the same layout that I'm showing right now. So I like this layout. Muscle memory, everything's where I think it should be. So that's handy. And you can also right click and you can customize this menu toolbar, and you can take any of these buttons here. If you see something that you find useful and you want it to be very easy to get to, you can just take these and you can drag them up here and put them wherever you want. So that's how that's the toolbar, and we'll get to know this more as we start modeling, but we'll move on from that for now. Up here is the menu bar. So this is pretty familiar with if you're working with pretty much any like Windows or Mac application. They all have this menu bar up here where we have file, edit, view. Insert is probably, if you're ever looking for a tool in the toolbar and you can't find it, I would just go to insert, and you can see our tools are all organized by these categories here. So that's a handy menu, and then calculate is also a handy menu. So yeah, that's the menu bar. And then I'm going to turn the tables back on. Down here we have the tables, which is basically you could model a whole model down here numerically if you wanted to in the tables. So we have the drop down here where everything's organized. This first option, structure, we can just go to that. And then under basic objects, you can see we have all of our basic objects. We have all of these tabs down here for each object. So materials, I only have one material defined. Sections, I only have one section defined. The thickness, these are all of our nodes. If you click on one of these down here, then that element will be highlighted up there. And you can also, never mind. Yeah, the element will be highlighted in the graphical view on anything that you select. So you can edit anything down here. For example, my member, I could change the member type or the section distribution. I could also create a new member if I wanted to. I would have to create a line first, but anyway, yeah, the table down here you can use to numerically model anything. So that's the table, and then this control panel we'll get into a little bit later with results. But yeah, so that's the basic overview of the program. And so now if you're planning on modeling along, this is where we will start. So I'm going to go up here and now we're going to create a new file. So you can either go up here to File, New, or you click on this New Model button here at the top left. So I'm going to click on that. And this is where we're going to create our continuous plate model. And this is our base data dialog box. And this dialog box in the first tab here will work with the first tab and make our way to the right. And the main tab is where we're going to name our model. So I'm going to name it continuous plate example. And then I'm going to put a random number at the end so I don't overwrite any of my other ones there. So that's the name. You can also add a model description. So yeah, you can do that, add a model description. And then also we have a projects tab here. So you can create projects. Basically, they're linked to a folder that's saved locally to your computer. So if I click on create new project here, can name it. You can have even higher folders where you can organize all your projects. And then you can choose where you want this project to be organized on your computer. So you just have to choose a file location there. And that's how you can create a new project. And then we also have the Doable Center where you can organize your project folders, but we're not going to get into this today. So I'm going to exit out of that. Next, we have the type of model. So you can create strictly 2D models and strictly 1D models in RFM. So for this example, it's going to be a 3D model. So basically what that means is that all degrees of freedom are accessible. So if we wanted to create a 2D model in the XZ plane, we could do that. And so we wouldn't have to worry about the rotation about the x-axis. Or if we chose an XY plane, those rotations would be locked. And then you can do just a 1D member example as well. So those options are there. We're just going to choose 3D. And those are, yeah, basically the main things that you want to choose there to get your model set up. This second tab here, as you can see, it says add-ons. Like Amy mentioned, the base program that we were just looking at here is for just the static analysis, giving you the general analysis of the model. But when it comes to design, this is where you would choose. You can see we have our design add-on category. So we'll be getting into this later with our other example, but this is where you would choose your design add-ons. We also have some other analysis add-ons. Good to know. This is our add-ons tab. We're not going to activate any now, but we are actually going to turn off. So this button or this option, combination wizard and classification. So if you have this checked on, the program will automatically create load combinations based on the selected standard that you have. So under standards tab here, right now I have under my standard group, I have the ASC 7 selected. You can see that we have we have a long list of international standards here that you can choose from. But for this example, I'm going to turn both of these options off because we're not going to be using any type of standard. So we don't need to select the standard under here, but this is also where you would select the standard for your design add-ons as well. This tab we can skip, and we'll move to the settings and options tab. Here you have some, if you want to get into the finer details of some parameters here for gravity acceleration, model tolerances, member representatives. We're not going to worry about any of this here. We're going to leave this all as default. What we will do and make sure is that the global axis system, I keep mine where the global z-axis is orientated upwards. I know internationally that differs, but this is where you can choose if you want it to be upwards or downwards. And then each element in RFEM, members, surfaces, etc., have their own local axis system, and that's denoted by a lowercase letter. And I want to keep my local z-axis set to upward as well. So that's where you can choose your axis system there, the orientation of it. One more thing before we click OK and have our model created are units. So units can be really changed anywhere at any time in the program. But we do, any of the dialog boxes you're in and you want to change the units, there's this button down here that says units in decimal places. And if I click on that, then we can see, so like, for example, I'm looking at the acceleration of gravity, which is in feet per second squared. And the nice thing about this units tool here or window is that you can see there are these red arrows. So whatever dialog box you're in, these red arrows will tell you what general point you're looking at, or general description, or whatever you're trying to change, it'll point to. So you can see gravitational acceleration here is being pointed at. But anyway, if you want to work in metric, you can change that here. So right now for this example and for this training, I'm going to be working in imperial units. But if you want to change to metric, you can go down here to this button called load save template. And you can see here you can set metric as default, or you can set imperial units as default, or you can just I could click on metric and click OK, and then everything will be moved over to metric. So that's where you can change back and forth between the two. And you can also, with this button, even create your own template. So if you change any of these units or decimal places here, and you want to keep those for all of your projects, you can create you can create a template, and then that template will be saved under the list of templates for your units. So I'm going to keep mine in imperial, and now we can click OK. And this will bring us into a blank model, and this is where we can start modeling. So right now you can see I have a blank grid here with my global axis system in the middle of it. You can see my model name here and the navigator data, and under my basic objects. I do have, under the basic objects, you can see here I have some materials, sections, and thicknesses that were carried over from previous projects. So that is nice, but for example purposes, it's not. So I'm going to delete them so we can learn how to redefine materials, sections, and thicknesses. So I'm going to delete them. If you see, yeah, we're going to delete them. And so now we don't have anything. Our model is completely blank. We don't have anything defined. Now we can start with some basics before we get into actually creating some surfaces and members. First thing to look at is you can see our grid here. We have our points here, and what we want to do is edit this grid. So we're going to go up here to settings of work plane, and under these settings we can edit or change the number of grid points that we have. So right now we have 30 by 30 in the positive and negative directions. I want to change that to 100 grid points. So I want 100 grid points in the positive and negative directions. And then you can also see you can change the spacing of your grid points. So right now I have mine spaced at 1 foot. And yeah, so you can change all of this, and you can also pretty much basically like the units that I was talking about, you can load a save template, and you can also save your own template. So if you edit these and you're going to be using them and they're all going to be the same for each of your projects, you can save a template. I'll just call it example, and then whenever you open a new model, you can set that as default, and then you can have a list of templates that you want to switch to, and then you don't have to always redefine this. So I'm going to click OK, and now you can see, hopefully you can see that my grid here is a lot bigger, and I have 100 grid points in each direction, and they're all spaced at 1 foot. So this just makes modeling graphically a lot simpler. Good to adjust your grid settings. And so now I'm going to show you guys how to model a surface. So to start off, there's plenty of ways to model a surface, but I think the most general way is to go to this tool up here. You can see right here the icon says new rectangular surface. That's what we're going to be making, is a rectangle. So we can just click on that, but I do want to just point out that there are other options if I click this drop down arrow right here. So we have rectangle, triangle, circle, and then this one, select boundary. You could create just some lines and then select those lines as a boundary and create a surface like that. But we're going to create a rectangular surface, and once I click on that button, you can see this new rectangular surface dialog box pops up. And first, we're going to choose our stiffness type here. We don't actually we can just leave the stiffness type as standard. There are other stiffness types that I'm not going to go over at the moment, but we will be talking about one of these later. Standard stiffness type is what we want to keep. And next, the next little section here says thickness with material. So this is where we don't have any thicknesses created. So we want to create a new thickness, and you can do that by clicking on this button here, create a new thickness, or I can just click on the box here. And this is going to open the new thickness dialog box where we need to define a thickness and material for our surface. So you can see there's other thickness types. We're just going to keep it uniform. Uniform. And now we don't have any materials defined yet in our file here, so we need to create a new material. And you can do that by just simply going to this button here, import from material library. You can create your own user-defined material, but we're not going to do that. We're going to import it in from our material library. So when I click on that import from material library button, this is our material library. And you can see here, I have it filtered by region right now to United States, but you can filter it to other regions. I'm just going to choose United States for this example training. And material type, you can choose any material type here. Concrete is what I'm going to go with. And then you can have it based on a standard. So I'm going to choose ACI 318 and 19. So now you can see after I filtered all of that, we're just down to concrete here. And I'm going to choose obviously concrete. And then I can choose the strength of the concrete. So I'm just going to choose 4,000 PSI for the concrete strength. Click OK, and now you can see we have our new material here created. We have our basic material properties here on the right-hand side. And there was one thing, yeah. So before we move on from creating this new material, this is strictly for example purposes, but you can check on this option here, user-defined material. And what this will allow you to do is you can see when I check it on, this new tab up here, stiffness modification, will pop up along with, yeah, that'll pop up. And then there's also this tab here, material values. And before we weren't able to edit these material values when this was checked off. So when that's off, you have your material values here, but you can't actually edit them. So if you want to actually be able to edit your material values, you want to check on user-defined material. And so now we have here our modulus of elasticity, shear modulus, Poisson's ratio, which is actually what I want to change. I want to change the Poisson's ratio from 0.2 to just 0. And again, this is just for example purposes for this training. This just allows us to get equal distribution of results across our surfaces. So I'm going to click OK. And now we have our material set for our thickness, and now we can choose the thickness. This one, these slabs are going to be 12 inches thick. And so now I can click OK. And so now we have our material thickness, and then we also have our thickness. So yeah. Now what we can do, you can see we have some other options here. We don't need to worry about them. We can simply just click OK. And so now you can see I have my cursor has changed to this reticle, and I'm able to snap to any of these grid points very easily. So now what I can do is all I have to do is tell the program, give it 2 points for this rectangular surface. So I'm going to left click on the origin here, and then I'm going to snap to I'm going to make this slab. Let's see, I'm going to make it 16 feet by 32 feet. So I'm going to go down here to 32 feet, and then I'm going to move up to 16 feet in the Y. Left click again, and now you can see we have our surface. So I'm going to right click, and that's going to, that right click anywhere is canceling out the tool. And yeah, so now we have our surface here. It is strictly a 2D element. It has a thickness, but you can see it's strictly just a 2D element. It's just lines, and we have our surface along with our 4 nodes to define it. And now what we want to do is create a couple more of these because we want to have 4 of them. But before we do that, I think it's easier to just move on, and what we want to do now is support this surface. At the beginning, middle, we want to have a middle span support and end support. So I'm going to add some supports to this surface. they're going to be line supports. So this whole first line here is going to be supported along the entire length. So up here we have a couple of different support options. Under this tool or in the toolbar, we have a nodal support if you just wanted to support one single node. We have our line support, and then we also have a surface support. So what we want to do is choose the line support option. And so this is kind of what I talked about in the presentation with FEA. With the workflow right now, we're defining our boundary conditions. So for our line supports here, this line support dialog box will pop up, and it's asking us to choose a line number. We can do that graphically, but we can also choose our line support too. So we have two predefined support options. We have a hinge support option where it's a hinge support. So the first 3 degrees of freedom, the translational directions are fully fixed, and only the rotation, all 3 degrees of rotation are released. So that's the hinge. And then we have rigid, where everything is just fully fixed. So that's what a rigid support looks like. And this is what a hinge support looks like. And you can also create a new line support. And you can define your own line support by choosing which degrees of freedom you want to be fixed. So if you want to fix something, you check it on. If you want it fully released, you uncheck it. So for this first side of the plate, it's going to be, we want to choose hinge. So we don't need to create a new user-defined one. We can just use the hinge one. And you might be thinking, oh, we didn't select our line number or the line that we want to assign this to, but I clicked OK, and you can see hopefully that there is a little icon next to my cursor here, and when I hover over any of these lines, it's letting me choose the line. This makes it really easy to just graphically assign supports to anything, so you can just graphically choose which lines you want your supports to go to. I'm going to right click and exit out of that. We also, so now we have this one side here fully supported along the line here. And what we want to also do is have another line support directly down the middle. So what I need to do is create a new line element. And I can do that by going up here to this tool, new line. So I'm going to click on that, and this window will pop up, and you can see I can just simply draw the line anywhere I want. Very handy right now. I can snap to the midspan of this line here, which is super helpful because I can just click on it, and then I can snap to the other midspan. So now I know that my line is completely in the middle of my surface there. So I can just keep right clicking to exit out of that. And now we want to assign our line supports, or we want to assign another line support to this line and this line. So we're going to go up here to the button again, assign line support. And we want to create a new line support because we can't use either of these. So we're going to create a new line support. And with this one, with this line support, we want it to be able to roll in the X direction, basically. So it's basically a hinge support, just it's able to move in the X translational direction here. A little more in depth with supports, you can see you can have a spring constant. So if that direction isn't fully fixed or fully released, it's somewhere in the middle, you can add a spring constant. And then there's also some non-linearities, which really get into the weeds here. We're not going to go over any of these today, but you can create some non-linear supports with each rotation and translational direction. But for this is the definition. We want the translational X direction released and our directions in the global Y and Z axes to be fixed, and rotation is all released. So we can click OK again, and now we want to select both of our lines there. And yeah, so now we have our line supports. We have this concrete slab here is fully supported the way we want it to be. So continuing on with defining our boundary conditions, now we want to load the structure, quote unquote structure. We want to load this concrete plate. And this is where we get into load cases and load combinations. So right now in this drop down here, you can see I have one load case, which is called self-weight. If I go to here, I can hit edit active load case. So and this will bring up our load cases and combinations dialog box. And I'm under the tab load cases, and load cases in the program, any loading or force that you apply to the model has to be assigned to a load case. So for this example, we only need one load case. We're not going to create any load combinations or worry about that right now. We're just focusing on one load case. It doesn't have any action type or anything. It's actually not even going to have self-weight. So in a load case, you can see here, self-weight is activated, but we can uncheck that. We don't want self-weight to be activated just for this example. And every load case is run according to a geometrically linear static analysis. By default, you can change that if you want. So all these calculations, static analysis for this example model will just be strictly linear. So we only need one load case, and it's going to be linear. So we'll click OK. And so now while under this load case, any loading or force that we apply to this model here is going to be assigned to that load case. So now we want to assign a loading to this. We want to put an area load on this entire surface here. And you can see here, this little section of the toolbar is where a lot of our loading options are. We have a couple different ones, nodal loading, align load, member loads, and a new surface load or surface loads. And a surface load is actually what we want. So I'm going to click on the new surface load button. And under this new surface load, we want to choose the load type, which is going to be force. We have some other options for load distribution. We're going to keep that uniform. And the direction is going to be in the global Z direction. So now we have our magnitude here. What is the magnitude of this loading going to be? And you can see I have it in KSF, kips per square foot. So I'm going to enter in kips per square feet what the magnitude should be. And for this, we're going to make it negative 0.210. Negative is telling the program what direction or what orientation in the z-axis the loading will be. And now we can simply either, if you know the number of the surface you want to assign the loading to, you can type that in here. For example, surface 1 is what we would apply to. You can also click on this button here to select the surfaces or surface graphically if you want. And then, so now if I click OK, I entered surface 1. You can see that our loading was applied to our plate here, our uniform area load, 0.210 kips per square foot. You can right click on this area load and there's a slider here if you want to just minimize the graphic. Yeah, minimize the graphic. It doesn't actually adjust the magnitude. If you want to adjust the magnitude, you can double click on it and you can edit it. So now our plate here is fully loaded, supported. And yeah, next thing to move on to is creating multiple plates now. So what we can do is take this one plate, we can drag from right to left to select the entire thing. And then we have a tool. We have some tools up here that are similar to something like AutoCAD, if you're familiar with AutoCAD. We have a move/copy tool here. So I highlighted everything and I'm going to choose that tool. And I want to create a copy of what I've selected here. So I'm going to create a copy. And the number of copies is going to be, we want to create 3 more of what I selected here. And now it's asking me how I want to displace these copies, where should they go. So we can use a displacement vector to tell the program where to put these, how to space out these copies. We want these copies just to follow a singular line in the X direction, and I want to have them spaced 5 foot from each other. So if our plate here is 32 feet long, I want to add 5 more feet to that to space them 5 feet apart. So I'm going to type in 37 feet here, and you could also just type in 5 feet here for spacing, but that's fine. So I'm going to click OK. And so now you can see we have 3 more copies of our example plate here. And I'm just going to take these, highlight them all, and I just want to drag and drop them, just move them over a little bit like that. And so now we have all of our plates here with the correct loading applied. So now, before we get into the rest of this modeling, we're approaching the 1 hour mark. So I'm going to switch back to the PowerPoint. And we're not doing this question yet. So if there's any questions, Siska, from the chat before we go to break that you weren't able to answer,
Hi, Alex.
Yeah. Hi,
we do have a questions. Can you show how to view the controlling load combinations when you have multiple say that you have multiple load cases or combinations and you want to find out the maximum deformation?
Okay. I might hold that question to later when we get into the results, if that's fine, just because we don't have we only have 1 load combination for this model.
Okay.
So,
yeah. That's fine. Then we can show that later.
Yeah. I'll hold that for later. So, is there any other ones?
No, that's it.
Okay. All right. Thank you.
Yep.
Yeah. So, yeah, we'll when we go over results, that will be in a later model. Then we can go over how to see the maximum deformations. But yeah, so now I think is a good time to take a 5-minute break. So we can come back here in 5 minutes. So yeah, take a break, use the bathroom, get some coffee, whatever you got to do, and we'll resume in 5 minutes. All right, so let's resume now. 5-minute break. So next thing we want to do now is create our concrete beam. I'm going to exit out of the tables just to give us more space here. Just making sure. Okay, yeah, so we're going to create a concrete beam now, which we're comparing our concrete slab here to. So to create a new member in RFM, you want to go up here to this button called New Single Member. And this New Single Member dialog box will pop up. You can see here we can choose the member type. We're going to choose beam. So this member type allows the member to take on both tension and compressive forces. So this is what you would choose if you were drawing a column or a beam. You would choose this beam member type because it can handle tension or compression, and it transfers full forces. So some other ones here, we're not going to go over any of these at the moment. We're going to stick with beam. And then under the second tab here, section, it's going to be a uniform section. And down here, we want to choose the section and the material. So the member start, you can see it says add member start, add member end. You only really need to focus on add member start to create your section of material. You can have your beam, you can have two different sections at the start or end. But we're just going to create a new section by importing it in from our section library. So if I click on that button, kind of similar to our material library, we have our section library here with our standardized sections. We have built up sections, thin walled sections, bars, massive, massive two. We're just going to be focusing on our massive rectangular section here. So we can click on that. And then we can choose the material we want. We already defined our concrete material here, so we can choose that and use it for our beam as well. And then in our second tab here, parametric massive, we want to choose our dimensions. So the base of our beam here is going to be 40 inches wide, and the thickness of it is going to be 12 inches. So you can see here we have this flat section here. And so now we can click OK. And so now we have our section and our material for the section start here. And you can also change the material down here. And then if you have multiple sections, you can choose them here. In the drop down, if you have multiple materials, you can choose them. And so, oops, sorry about that. And so now we're going to click OK. And basically, I just want this beam to also be 5 feet from my slab here. So I'm just going to start drawing it 5 feet from the slab. So 1, 2, 3, 4, 5 right here. And it's going to be 32 feet in length in the X direction. Add a node, or I could add a node by simply going to create a new node, and I could just click on the midspan there and add a node. Or you can also right click on a member and go to members, and then we can go to divide member, and then we can divide our member either by a distance, or we can divide it by a number of nodes. So I'm going to choose this intermediate, a number of intermediate nodes. I simply just want to add one node to the midspan. There's some options down here. I want to check on this option. I want to create this node as an on-member node, and this allows me to add the node without dividing the member. So I'm going to click OK. And so now we have this node here. You can see, hopefully you can see, if I change this to a wireframe view, you can see that this node here hopefully is blue. or hopefully you can see that it's blue. And what that means is that it's an on-member node type. So it's simply just there for defining our line or for defining our nodal support. You can see these red nodes here on the surface lines and the member line there. That red means it's a standard node, which is just to define the boundary of the line. Okay, so now we're going to choose nodal support again. And this time we actually want to create a new nodal support. And now we want to do for this support is we also want it to be rolling in the X direction. So we can click OK for that. And click OK again and add our node there. And we also want to do the same thing for our end node here. So they're rolling or released in the X translational direction. And one thing to note for this beam here is you can see that for this beam or for this member, it is fully released about its local x-axis. As you can see the local x-axis here with each of these nodal supports. So if I tried to run this, if I tried to run the results for this beam, I would get an instability because in the program's eyes, this member here is able to just infinitely rotate about its x-axis. So at least one of these supports needs to have the rotation about the x-axis fixed. So what I can do is I can double click on this first support here. I can edit it, clicking the little hand there, which indicates editing it. And I can simply fix the X rotation. So that's what it looks like when the X rotation is fixed. So I'll click OK. Click OK again. And so now you can see it's fixed there. And so now our beam is supported how we want it to be. And so now that we have all of our elements here supported, now I want to get into talking about FE-Mesh. Once you get all your boundary conditions figured out with loading, sorry, I did forget to load this beam. So we don't have any loading on it right now. I actually do want to do that. So for a beam, for a member, it's not as straightforward with the surface. There's the new line load tool, which you can't use for a member. The new line load tool is used for mostly defining line loads on the parameter of a surface. For a member, you want to use the new member load tool. So we'll click on that. And under new member load, this looks very similar to the new surface load. We can choose our load type, which will keep as force. We'll keep it a uniform distribution in the z-axis direction. And this load magnitude is going to be the exact same magnitude as the slabs that we have. So negative 0 point, notes real quick, negative 0.210, and this is going to be kip per feet. So we can click OK, and we can select graphically our member here and click OK. And so now you can see we have our member load here of 2.1 or 0.21 kip per feet. Okay, so now I want to get into FE-Mesh. Down here, there's some buttons. I want to turn off the grid just to make it a little more clear. And then up here, I can turn off the showing of our loads. So once you're done modeling with everything, you want to adjust your FE-Mesh depending on the size of your model. So there is a global FE-Mesh setting, which is up here under Calculate. You can also find it at this button here. Normally by default, this button just says Display FE-Mesh. We can click on that and generate our FE mesh based on the default global FE mesh setting, which for imperial units is 1 foot by 1 foot. So each of these FE mesh blocks here are 1 foot by 1 foot, which actually looks really good for our plates here. If you want to adjust this mesh setting, you can hit this drop down arrow, and under mesh settings, actually it's set to 1.5 feet. So that's our target length globally for our whole model. I do want to, for example purposes, adjust the FE mesh length for each of these plates. And so if you wanted to, let's say, adjust the FE mesh for one single surface, you can do that using what's called an FE mesh refinement. So in the left panel here in the navigator data panel, we can go to, so logically, if you're looking for this FE mesh refinement for a surface, you would think, okay, let's go under types of surfaces. We have some types of surfaces you can create here, and one of them says surface mesh refinements. So I don't have any defined right now, so I need to create some. So I'm just going to double click on it, and this new surface mesh refinement box will pop up, and you can see it's creating one by default. The target FE length for this first mesh refinement, let me just look at my notes real quick. Yeah, this first one's going to be, we'll make this one 7 foot. And then down here, we can click on create new surface mesh refinement. So now we can have multiple definitions. This one's going to be 4 feet. Create another one. This one's going to be 1.25 feet. And then our last one is going to be 0.4. Oops, did not type it in, 0.4. So now we have all of these FE mesh refinements. So let's say I just click OK. Oh, I typed it in up here. Okay. Yeah, no. So click OK. And so now on the left here under surface mesh refinement, if I expand this, you can see that they're all blue. So if you see anything that's blue inside of your data navigator here, that means they're not assigned to anything in the model. So they're all blue, they're not assigned to any surface. So what I can do is just right click or double click on one of them. And you can see here, I can go up here to assign to surface number. You can select this graphically, or if you know the surface number, you could just type it in. So I can select this graphically. I want to select surface number 1 here for our 7 foot FE mesh length. 4 foot, so like I said, if you know the surface number, that would be 2. And then this next one will make 3. And then this next one, I'll just type in 4. I'll click OK. It's telling me I need to delete the mesh because obviously I'm making new mesh refinements. And so our mesh is deleted. You can see these symbols here. I made them yellow, and they're letting you know that there's an FE mesh refinement assigned to the surface, and you can kind of see, you can get an idea of how large that FE mesh length is based on the little symbol. It changes depending on the length. And now let's say, yeah, so now we have our FE mesh refinements. I'm not going to generate the mesh yet, just we'll get into that. The last thing I do want to add before we get into the results is a results section to just better analyze the internal forces of our surface and compare them to our beam here. So I'm going to go up to this button, set new results section. I'm going to click on it, and this is where we can create our results section or create a results section. Basically, there's different types here, 2 points in a vector, that's fine. Show a results section and direction, we want it to be in the positive local z direction. And then all we need to do is define 2 points to create the results section. So you can type in the coordinates if you wanted to. You can select each point individually, but there's this button here that I can use to select 2 points graphically. So very easily I can snap to the midspan of the plate here, which is very helpful. So I'll left click on that, and then I'm going to snap to the midspan at the end here. So now my results section is going to go through all of my surfaces here. Projection and direction, we want to project in the global Z direction. So now we can click OK. And now we have our results section through all of our surfaces. And so now this is where we can run our results. So once you're finished with adding everything into your model that you need to, you can run your results. There's a couple ways to do that. Easiest way is to just go up here and click on calculate all. So click on calculate all. What it's going to do is now it's generating our mesh, and we only have one load case, so should be pretty quick. It's just gonna calculate that one load case. And now we have our results. It automatically goes to our result tab and our result nav, and the navigator on the left-hand side here. By default, the first thing that's shown is our global deformations and the resultant direction. I can click on this cube up here, and we can get a look at our deformations and do a visual check of our deformations. So all of our deformations here basically look like how I would expect them, how the deformations I would expect to look for the loading and some boundaries that we've included here. So a good visual check of the deformations just to make sure your modeling is correct is always good. You can see the panel on the right-hand side here giving you the color scale. So our max deformation is 0.02 inches. So yeah, that's the result of the one load case. I know there was a question about seeing the maximum if you have, so the question was, if you have a long list of load combinations and you don't want to manually go through each load combination to see which one is showing the maximum deformation, what you can do is I'm just going to switch back. I'm going to switch to the other model real quick. And you can see here in this other model, if I go to the load cases and combinations dialog box, you can see I have multiple load combinations, and I also have checked on my standards for combination wizard and classification, which will automatically, based on the standard you select, automatically create load combinations based on that standard. So here we have our multiple load combinations, taking all of our load cases and combining them. And then what that does is under this design situations tab, you can see here we have our strength limit state design situation, which takes all of the strength limit state load combinations, adds them, or goes through them and chooses the minimum and maximum values. So this is a little further ahead than I want it to be, but we can just show that real quick. So if I can just run the calculation for this model real quick. And you can see it run through the mesh. The nice thing about RFEM 6 is it can take advantage of multi-threading with your CPU. So you can see it can run all of the load cases and combinations at the same simultaneously. So it's running through our load cases and combinations. You can see your convergence diagram on the right-hand side here. And so now if I go under this design situation for LRFD or our strength design, I'm right now showing the maximum deformations. And let's say like the question was, what is the maximum deformation for our strength combinations? I would find that under here. So envelope, since our design situation 1 here is an envelope solution, right now it's showing the maximum and the minimum values. I can show strictly the maximum deformation values. And then if you want to know which load combination that is based on, if I turn my tables back on here and I go under the, let's see, static analysis overview, I would want to go under, well, you would choose, let's say, results by member, global deformations, and then we would want to choose design situation, and it should say somewhere which load combination. Oh, course period. So you would find your maximum displacement and it'll tell you the corresponding loading that is corresponding with that maximum deformation. So hopefully that answers the question. There might be a better way to do this, but this is the way I'm familiar with. So here you can see your deformations and you can see the corresponding load combination. So
Alex?
Yeah.
Can you go to the overview quickly? I think that might be a little bit more straightforward.
Okay. Yeah, I think you're
So
actually right.
here it just gives you the maximum, like it says CO2, CO3 right on the side too. If you don't care about like looking at each member or each surface.
Yeah, thank you, Siska. That's a good point.
Yep.
Yeah. So thank you.
Thank you.
Thanks for that. Yeah, this is the maximum displacement in each of the directions. And I didn't realize, yeah, you can see the which load combination that corresponds to right there. So awesome. That should answer your question, and we can get back to the example here. So now you should be able to see, let me just check. Okay, so now we want to compare the results of our plates here with the result of our member. So I could turn off global deformations here by checking off this box. And I can also turn off our results section for now. I want to turn on results for members. So let's say for this beam here, I want to see the internal forces for this beam. So I can check on members and then I can expand internal forces. Right now it's just showing our axial forces, which we don't really have any. So that makes sense because we just applied a uniform load. So what I want to do is check on MY. And this is the moment. So you can see the Y is lowercase, which indicates that these are the moments about the local Y-axis of the member, which if I right click on the member, you can turn the local axis system of the member on or off there. So makes it a lot easier to just understand what you're looking at or the orientation of the axis, the local axis system. And so, yeah, this is our moment diagram. And I want to compare this to the results of, or the moment along our surface here. So if I turn on surface results simultaneously, I can go under internal forces. And under internal forces, I want to show the moment along the local axes, the local x-axis of my surface. So our surface has a local x-axis as well, and you can turn that on or off by right-clicking on any surface and turning it on. And so I'm going to check on moments, mx, which is our moments along the x-axis here. And now what I can do is turn on down here our results sections. And so now we can get an idea of, if I move this panel, I'm actually going to exit out of this panel. We don't need that right now. Now you can kind of get an idea of how FE mesh really affects your results, because if I turn off results for a second, we can see that the FE mesh is very coarse, super coarse for this panel here. And we go down the line, and this panel, or slab, you can see that the FE mesh is super fine. So really the question is which FE mesh is the correct one to use. And I always say the rule of thumb when it comes to surfaces and FE mesh is that you want to have at least 4 FE mesh elements in each direction. So this first one here, kind of have 4 in one direction, definitely don't have 4 in the other. This one here, we have 4 in one direction and more than 4 in the other direction. So this is kind of getting into the correct idea. Another good rule of thumb when it comes to FE meshes is you want it to be as fine as necessary, but as coarse as possible. So if I turn on the results here, and I'm going to go down here to results sections and turn on local extremes so we can see the maximum moment. You can see the maximum moment for this one is 8.44 kip per feet. But the finer the FE mesh gets, you can see how much that actually gets closer and closer to our control beam here, which the maximum moment for our control beam here is negative 6.7 kip per feet, or kip feet. I said kip. Yeah, negative 6.7 kip feet is the maximum moment here for our beam. And you can see the finer our mesh gets, the closer that our maximum moment for our slab here gets to that 6.706, 6.70. Yeah, so you can see why it's important to have your FE mesh as fine as necessary, but as coarse as possible. You may be asking, okay, well, I'll just make my FE mesh just super small. Small, like, what does it matter? I'll just make it super small for any of the slabs. And that's fine, but you have to keep in mind that the smaller your FE mesh gets, the more computational computing power that takes to run the calculation. So you can do that, but if you have a large model with a lot of surfaces in it and you make your FE mesh super small, your computation time or your calculation time is going to take a really long time, and you might not even really be getting that you might not even be getting that much more accurate of results, because you can see between these two, this one's 6.72 and this one goes down to 6.7. So that's up to you as an engineer to determine, that's up to you to determine what accuracy you think you need. So good rule, have at least 4 FE mesh elements, in each direction on your surface. And a good phrase to live by is you want your FE mesh as fine as necessary, but as coarse as possible to save time in the calculation. So this kind of shows you how FE mesh really affects results in your model. So always good to keep that in mind. We can also take a look by right-clicking on our section here. We can take a look at our result diagram, which you can do for members as well if you really want to get into, if you really want to see in detail your shear diagrams and your moment diagrams. But this just kind of really shows you how the FE mesh, like the finer it gets, the more accurate, the more points of data we have along our diagrams here. So always just cool to see. Next thing to talk about is you're wondering, okay, this difference between these two, it could be well, the next subject I want to get into, actually, forget about that. The next subject I want to get into is hand calculations and comparing hand calculations to results in the diagram, results in the program. If you're running a hand calculation for this beam, you're probably seeing something a little bit more, just a tiny bit more than what, or a tiny bit less actually, than what the maximum moment is for this beam. And you could chalk that up to rounding errors, or not having the most accurate, or having the most significant figures when you're calculating. But really what that comes down to is stiffness deformations and how the program takes into account stiffness deformations. Whereas with hand calculations, we don't take into account stiffness deformations. We assume that the shear deformations, I'm sorry. We don't take into account the shear deformations in our hand calculations. We assume an infinite shear stiffness. So what the program does is assume that there is shear stiffness. And so the results are going to differ a little bit. And I'm going to go back to the PowerPoint to explain this further. So let's move. I did have a question actually I wanted to post for you guys. Oops, you might be seeing the answer. Okay, so the question before we get into shear stiffness and plate theory is, well, actually it is a fill in the blank kind of. So the FE mesh size should be, and if you could list the answer in that same questions panel, we can go over it. All right, so I'm seeing some answers. Yeah, most of you guys are correct. So let's go over it. FE mesh size should be as coarse as necessary and as fine as possible. B, as fine as necessary and as coarse as possible. C, as precise as possible and as coarse as necessary. So the correct answer is B, which you guys got. So you want it to be as small as you possibly can make it, so as fine as necessary, and as big as possible, as coarse as possible. You know, you don't want it to be so small that you're really not getting that much, it's diminishing returns, you're really not getting that much more accuracy, and your calculation time is taking forever. So you want it as fine as necessary, but then you want to find that happy medium where you're getting good accurate results, but your calculation time isn't taking that long. So B is the correct answer. Okay, so now we're gonna get into plate theory, and to talk about plate theory, and I'm going to use an analogy to beam elements or beam theory. So the first beam theory is Bernoulli's, and with Bernoulli's, With Bernoulli's, this theory assumes that the cross section remains in plane and is also perpendicular to the member axes. We assume for Bernoulli's that there is no consideration, we don't consider any shear deformations, and that the shear stiffness is completely rigid. So that's Bernoulli's beam theory. And now let's compare that to the Timoshenko beam theory, where the cross-section remains, we assume that the cross-section remains in plane, but we don't, but it's not, it doesn't remain perpendicular to the member axes. So we assume that, and by assuming that, we are taking into account shear deformations, and the shear stiffness is limited and isn't completely rigid. So you can see how the deflection is going to change based for these two theories. When I say that the member axis does not remain perpendicular to the member axes, you can see that for Bernoulli's that the cross section remains completely perpendicular with the member axes, whereas for the Timoshenko theory, we have our member axes, but our cross section does not remain completely perpendicular. We don't assume that it remains completely perpendicular to our member axes, which leads to more accurate results, but also a higher bit deflection for the Timoshenko beam theory. So now I want to compare those two theories to plate theory. So the equivalent analogy for plate elements would be the Kirchhoff plate theory. For the Kirchhoff plate theory, we assume a geometrically linear deformation, and we assume linear elastic material is being used. So that's based on Hooke's law. Then we assume that the cross sections remain flat and there's no warping. There's a constant thickness. And most importantly, there's no consideration of shear deformations when it comes to the Kirchhoff plate theory. So no shear deformations, basically pretty similar to Bernoulli's theory. For the Resner-Mindlin theory, this is similar to the Timoshenko beam theory. The first couple assumptions here are the same. The only assumptions that really change for this one is we do consider shear deformations in the Resner-Mindlin theory, and we also take into consideration transverse/lateral strains. So I'm sure you guys are familiar with transverse lateral strains. We have this rod here, and as the rod is being pulled in tension, the cross section is shrinking because of the transverse/lateral strain. And so this is being taken into consideration with the Resner-Mindlin theory for plates. So those are these two theories are used in RFEM. And so when it comes to plate elements, the Kirchhoff theory, again, no consideration of shear deformations. This theory is good for thin plates, like thin steel plates, something like that, where like they're not super thick, so you're not losing really any accuracy in your results, and it's a simplified approach. So that's the Kirchhoff theory. Resner-Mindlin theory, you get more accurate results because you're taking into consideration shear deformations. And so if you're modeling something like a thick concrete slab or like a foundation slab or something with a lot of thickness, then you want to, because the more thick the element is, the more your results are going to change because you're taking into consideration those shear deformations. So the shear influence for a component is very high for thick plates. If you're neglecting shear deformations for super thick plates, then you're going to have some significant errors in your results. Higher value approach, you're going to have higher deformations, higher deflection, higher shear forces, but this is more accurate. So that is play theory. So I'm going to go back to RFM. And how does this, what does this have to do with RFM? So under the results, under my load case here, if I go to edit active load case, we can change the theory that's being used for our calculation. So under our load case here, that we're running our static analysis setting, our first one here. If I edit this, I can go under the basic settings tab, and I can change between the plate bending theory, Resner-Midland, or the Kirchhoff. So if I change this to right now, shear deformations are being taken into account, all of that. Let's say I change this to the Kirchhoff, and it's going to ask me, it's going to tell me you need to rerun your results because it's running a different theory. So now you can see, like I mentioned, before this was 6.70 something. Now we're at 6.72 moment because we are now not taking into consideration shear deformations, and we're assuming the shear stiffness is infinitely rigid. And if you're wondering, can we do the same thing with beams and members? We can. If you don't want to take into consideration shear stiffness and you want to compare this to hand calculations and just see if they match up, you can edit your section here and you can turn on this option called deactivate shear stiffness. Again, it's going to ask you to rerun the calculations. We can do that real quick. And now you can see we are matching up now between our surface and our beam here. So that is plate theory and how it affects results in RFEM. So that is the first model example, and everything about FE mesh and plate theory. I know we have 10 minutes left, so I'm going to look. Well, is there any questions that I can answer, Siska, in the chat?
Hey, Alex.
Yeah.
Can you show how to export the result to Excel?
Yeah, I can do that. So yeah, let's say you want to export results from RFM to Excel, which is very easy. I'm going to go up here and turn my table back on. So that's actually, yeah, we should go over table results too. So static analysis, we're in the overview. This kind of gives you a sum of your results here. Let's say we go under results by member. Let's just keep this simple. I'm going to highlight this member and I'm going to create a visibility by selected objects. So now we just have our member here. Let's say I want to go under internal forces here. So in the table here, you can see we have our member number. We're looking at member number 1. We have our node numbers here, location. We got our forces. Let's say we want to export this to Excel. So there's a button right here called Export Current Table, and it looks like Excel. So this button allows you to, it's going to open my Excel. And yeah, this is how you can export results from RFM to Excel using the tables.
Okay, thank you.
There's no
other questions.
Okay, all right, sounds good. I'm not going to save this. So yeah, tables. Yeah, I didn't really go over the tables too much. For results though, yeah, you can view results by node, by line, member. Yeah, so that's how the tables work. And this is basically it for this model. So what I'm going to do is start the other model. And the other model, I'm not going to start from scratch. I'm going to open a I previously made this model. We're not going to remodel everything, but we are going to remodel some things. And so if you want to follow along with me, you can under the chat window in this go to training. I included a link to our website, our webpage, where you probably want to register for this training. And I'll click on that now and show you. So if you are on our page here and you want to follow along with me, I uploaded this model to our page here. So it should be at the bottom here. Let me just refresh. It is, it doesn't look like this is the official last model, but it doesn't, oh, here it is, okay. So template design add-on example. You can download this from our website, which you can also see there's a lot of other models you can download from our website if you are interested in checking them out. But you can download this one if you want to start with me, follow along with me for this one. So that link is in the chat, and we don't really have too much time left before 2 o'clock. I'm just going to look at some other questions real quick. The lesson, yeah, this is recorded, so it will be posted later this week on our website. It should be posted under the same link that I just included on our website. So you can always come if you can always come back to it if you want. So yeah, so this model, I'm gonna go back to the PowerPoint real quick and just explain it. We'll go over this. Actually, no, this would be a good time to go over these questions. So let's go over this question. So the plate theory of Kirchhoff does consider shear deformations. So this is a true or false. If I can get there we go. So if you could answer this in the questions, then we can go over it. All right, nice. So you guys are all correct. Yep, it is false. So the plate theory of Kirchhoff, it says the plate theory of Kirchhoff does consider shear deformations, and that is false. It does not consider shear deformations in the Kirchhoff plate theory. So yeah. Next question. Where is the stiffness modified? Oh wait, no, sorry, we're not doing that question. Not yet. I want to go back to this question. Oh wait, no, not this question. Oh, that was actually the only question I had before we start the other model. Never mind. Okay, so good. Yeah. Now we can, oops. This next model, I'm probably just going to explain, I think I'm just going to explain this next model and we can just get into it tomorrow. So this model is our design add-on example. With this example, we're going to cover topics like load transfer surfaces. So that's a different type of surface where you can create the surface. It adds no additional stiffness to your model. It's strictly for distributing loading to members using uniform area loads. So we'll get into that tomorrow. Load case creation, we'll get into that based off of the standard. Some more element manipulation tools from that are similar to things like AutoCAD. And then the main topic will be design add-ons. So, and then we'll interpret some results, static results, similar to what we just covered, a little bit similar to what we covered today, maybe a little bit more in depth. And then timber design, steel design, and concrete design we'll go over. We're going to keep it simple with these designs or design add-ons. We're not going to get too in depth. We're just going to be designing these 3 concrete columns here. And then we're going to design a couple, 1 or 2 of the joists, timber joists here in this mini structure. And then we're going to design 2 of these girders for the steel. So yeah, so that's going to be the plan for tomorrow. Are there any other questions yet before we conclude for today?
No question, just for the recording and the certificate, which we will send to after the 2-day training.
Yep. Thanks, Siska. Yeah, so we're not going to send that out tomorrow, but probably, yeah, you'll look out for that through email later this week. So that's it for today. If you have any questions for later today or before tomorrow and you want to email us, feel free to email us. This is our technical support email. We have a lot of people that look at this email, so feel free to send in questions, models. That's free, and our phone number is here. And yeah, thanks for everyone for participating today. I look forward to seeing you all tomorrow, and I hope you have a good rest of your day. Thank you.